Well, my dear students, now we are to start 37th lecture in the series of mechanics of metal forming, and if you recall, we started the finite element method, and the last time uh, the application of finite element method concept was dedicated with certain examples, like we took the the truss elements, truss problem, and also we took bar element bar problem, and so we would further extend in this lecture number 37 the 2D examples as well, and let us make the concept much wider, and then at the end we would be giving you maybe in 38 or 39th lecture the 3D metal forming problems. Switching over, I am taking these problems different varieties to also give message that this is not only applicable to metal forming, but it is applicable to all sort of area that I mentioned earlier. So, starting with the last lecture, where if you look back, the two-dimensional problem where the basic theory, in fact where the general stresses and strain in a structure, which if you look at, so basically it consists of the stresses as 6 component, right, sigma x, sigma y, sigma z, and shear stresses, that is the tau xy, tau yz and tau zx. So look at this figure, 3-dimensional cube where these direct stresses sigma x, sigma y and sigma z and the shear stresses on the faces are there. So under certain, and the 6 corresponding strains would be epsilon x, epsilon y, epsilon z, and the corresponding shear strains, right. So under certain conditions the state of stresses and strains can be simplified. A general 3-dimensional structure analysis can therefore be reduced to a 2-dimensional analysis, right. So if you look at this figure here, where the plane stress problem of 2-dimensional nature is shown, because the case is plane stress, therefore the equation 1 if you look at, that means the sigma z and the tau y z and the tau zx all are equal to 0, because the strain z in z direction is 0, and strain in z direction is not equal to 0, because it is a plane stress. So a thin planar structure with constant thickness and loading within the plane of the structure, like here it is shown in xy plane, you can look into, it's a cylindrical case, cylinder case, and having internal, and there is internal pressure. We took this example while discussing the case upper bound solution. So if the same problem is taken as plane strain, then that means the sigma z is not equal to 0. If you take the plane strain in z direction, the stress is not equal to 0. That means if it is plane strain, That means if you recall back, that means epsilon z and the shear stress, that is yz, and shear stress zx are all 0. So that's a long structure with a uniform cross section and transverse loading along its length, that is in z direction, is shown here. You can look at this figure. So the stress strain along with temperature constitutive equations can be written here as 3. That shows the for elastic and isotropic material one can have this stress strain relationship. So that is shown here in matrix form, equation number 3, where sigma epsilon x, epsilon y and corresponding shear stress is shown, and then the corresponding matrix that has the K matrix, that is the and then the stress and other thing that is whole. So that means the strain is defined as E inverse sigma plus, that is the epsilon the strain, corresponding strain, where if it is epsilon 0, then it is the initial strain, that is at the 0 initial strain, and whereas capital E is the Young's modulus. And if you look at the figure where the Poisson's ratio nu is shown, and G can be that is the shear modulus, G can be shown here as shown in equation number 4, that is the G is E by 2 1 plus nu, which means that there are only 2 independent materials constants for homogeneous and isotropic materials. So one can also express the stresses in terms of strain by solving these equations, that is equation number 3 and 4. So one can write down the corresponding stress equation, and this what has been shown in 5. So it is just substituting the values in the equation number 3, and then one can find out the sigma x, sigma y and tau xy vector, that is the stress vector is equal to corresponding the Poisson ratio matrix and the other thing. So the stress is nothing but it is equal to E epsilon plus sigma 0. Sigma 0 is again the stress at the initial stress, because there is, when there is no strain, sigma 0 is the stress. Okay, so that's the relation. These relations that has been shown in 3, 4, 5 are valid for plane stress case, and for plane strain case one need to replace the material constant in the above equation in this following form, which is given in equation number 6, right. So one should be careful, like the corresponding things are to be changed as compared to the stress case. So E has to be replaced by E by 1 minus Poisson's ratio, that is the tau square, and then the Poisson's ratio has to be replaced by Poisson ratio divided by 1 minus nu, and G has to be same because it is a material property. So for example, the stress is related to the strain by this equation, that means the sigma z, sigma x, sigma and y and corresponding, now it is related with this, and this is what's the plane strain case. So now you compare the plane stress case and plane strain case, it is quite different. So initial strains due to temperature change can also be included, so that we call it as the thermal loading. So that can be written as whatever has been shown here in equation number 7, all right. So that means epsilon x0, epsilon y0, and the shear strain xy0. So that is the vector form. It is alpha delta t, and 0, where alpha is the coefficient of thermal expansion, and delta t is the change of temperature. Please note that if the structure is free to deform under thermal loading, there will be no elastic stresses in the structure. All right. So this has to be taken care. Now the strain and displacement relation can be there, because once we have stress strain, so the for small strain if it is, and for small rotation as well if it is there in this problem. So one can write down that the epsilon x, that is the strain in x direction, can be written as, if the displacement is u, so du by if it is deva, rather very small infinitesimal displacement, so deva u by deva x, and then similarly epsilon y would be deva v by deva y, and the shear component, that is the xy shear strain xy would be deva u by deva y plus deva v by deva x. So this can be shown here in matrix form, and it is shown here in equation number 8, right. So that is the epsilon x, epsilon y, and the shear strain xy, and that is what is been shown, and that is nothing but equal to the strain vector is equal to capital D u. So from this relationship one knows that the strain and thus the stresses are one order lower than the displacement, and if the displacements are represented by polynomial, then accordingly one can, so the one order lesser. Now let us see the equilibrium equations. As you know, in elasticity theory, the stresses in the structure must satisfy the following equilibrium equation, and this equilibrium equation is shown here in 9, because it is two dimensional. So the two equilibrium equations, that is the deva sigma x by deva x plus deva tau xy deva y plus fx is equal to 0, and deva tau xy deva x plus deva y plus fy is 0, where you know fx and fy are the body forces, like it is a gravity forces, and it is in per unit volume. In fact, in finite element method, these equilibrium equations are satisfied in an approximate sense, right. So it has to be satisfied. Then next we come to the boundary conditions, right. So look at this figure. This is a domain, 2D domain of interest, where there is a traction Tx Ty, and on a part of the surface Su, and then there is a pressure, that is the, so the boundary S, if you, the whole boundary S of the body can be divided into two parts, one as your Su and St. So the boundary that the conditions are therefore is very much important. So if you look at the boundary Su, where the u, that is the displacement, is u bar, and v is the v bar if it is, and similarly on the boundary T, the displacement, the traction is your T is Ts bar, and Ty traction is your Ty bar. So in which as I told, these are the traction forces, that is the Tx and Ty's. It is a traction forces or it is the stresses on the boundary, and the bad quantities are that is the bar which is there are those with the known values. Alright. So, in finite element method, all types of loads, like it can be a distributed surface body load, or it can be a body forces, it can be concentrated force, and it can also be there the moments, etc. So, it has to be converted to point force acting on the nodes, right. This is what is the practice. So, exact elasticity solution if you look for. So, these exact solution, that is for the displacement, strains and stresses of a given problem must satisfy the equilibrium condition. This I have already told you earlier, and if you recall back the just we equation number 9 which we discussed, the equilibrium equation, the given boundary condition now which is shown as shown in 10, and the compatibility condition, that is the structure should deform in a continuous manner and there should not be any crack or overlaps in the obtained displacement field, and this is what is called as your compatibility conditions. So, these things are to be satisfied for getting exact elasticity solutions. So, with this basic for the two dimensional, the stress strain including the temperature into picture, let us take this example. So, in this example there is a plate which is supported and loaded with the distributed force P, right, and which is shown here. The material constant therefore are capital E and Poisson's ratio nu. Alright. So, the exact solution for this simple problem can be found as we have already explained. Let us see how one can get the exact solution. So, let us see how to calculate u. So, what is u? That is the displacement. So, displacement u is the P by E x, and the if you see in y direction and displacement along y direction if it is taken as v. So, u can be P by E x and v can be minus nu P E by y, and similarly the strain, that is the epsilon ix can be P by E, epsilon y can be minus nu P by E, and the shear strain, that is xy shear strain, is 0 because it is the plane case, right. So, the stress one can then write down, that is the sigma x is P, it is already there, and sigma y is 0, and the tau xy is also 0. So, exact or analytical solution for simple problem like this are numbered, like the suppose that there is a hole in the plate, right, if it is. So, that is why we need finite element method to solve it, right. So, to start with the finite element formulation for this particular 2D problem, so one has to be a general formula for the stiffness matrix as the practice you remember. So, the displacement that u and v, the displacement in a plane element are interpolated from the nodal displacement, that is u and v, right, using the safe function ni. If it is safe function is taken as ni at ith node, so one can write down the interpolation for the displacement. So, the interpolated UV vector for the displacement can be written as shown here in equation 11, that is means U vector is equal to capital N, that is the shape factor vector, and D. So, D is the displacement vector, that means U vector has got U and V, the shape factor capital N is your N1 0, N2 0 and so on, and the second row 0 N1 like that, whereas the displacement vector is U1 V1, U2 V2, U3 V3 like that. So, it depends on the number of elements. So, the N is the shape factor matrix, that is what is there in equation 11. U is your displacement vector as I told, and D is your nodal displacement vector. Okay. So, here we have assumed that U depends on the nodal values of U only, and V on the nodal values of V only, not anything else, right. This has to be noted. So, for strain displacement relation that we gave it in equation 8, if you look back, the strain vector is what? It is what is the capital D du, and that can also be written as capital D, capital N D, or the strain would become as capital B D, that is shown in equation number 12, where capital B is your strain displacement matrix, and that is given by capital D, capital N, right. So, this is what we discussed earlier as well. So, consider the strain energy stored in an element where capital U we calculated, and that was given as half of the integral over the domain, that is the sigma T epsilon dV, and that is equal to half of the sigma over domain, that is the sigma over the domain strain stress strain plus because there are two boundaries. So, the stress strain for the boundary 1 and then the boundary 2 and the other, if it is there is any strain there. So, that is volume, and that simply the strain energy, simplify the integral and all those things and put the whole thing in the matrix, it becomes in the vector form as half of dt k d. So, from this one obtains the general formula for the element stiffness matrix. That means, it becomes k, that is the element stiffness matrix, is equal to integral over the elements integral bt capital E capital B dV, that is the volume. Please note that unlike the 1D case, capital E here is a matrix which is given by the stress strain relationship, equation number 5 if you recall back. So, for the plane stress condition, right. So, the stiffness matrix K here, which is shown in equation 13, is a symmetric, since capital E is also symmetric, right. So, also note that given the material property, the behavior of the stiffness matrix K depends on the B matrix only, which is in turn on the shape function, right. So, thus the quality of the finite element method is representing the behavior of the structure is entirely dependent by the choice of the shape function. That is true, I told you earlier. So, most commonly employed 2D elements are linear or quadratic triangles and quadrilaterals, as I told you, right. So, if we see a constant strain triangle, that we can short, we say it CST or T3 also it is called as in technical word. So, this is the simplest 2D element. CST element, which is also called as the linear triangular element. So, this is what has been shown here in this figure, and please note that this constant strain triangle, we have node 1, 2 and 3. The coordinate system is xy. So, for this element, as you look at 3 element at the vertices, 3 nodes at the vertices of the triangle, which are numbered around the element in a counterclockwise direction, right? And each element has 2 degree of freedom, and that is in x and y direction. The displacement u and v are assumed to be linear function within the element. That means u must be equal to say b1 plus b2x plus b3y, right, and v must be equal to b4 plus b5x plus b6y. That is what has been shown in equation number 14, where bi's, that is I can vary from 1 2 3 6 like that, are constants, right. From these the strains are found to be therefore, that is the epsilon x is equal to b2, epsilon y is equal to b6, and the shear strain xy is equal to b3 plus b5. Alright, this is what is shown in 15. These are the constant throughout the element, right, these b2, b1 and all those things. That's one has the name, that is which comes as the constant strain triangle CST. That's the meaning of meaning. So, displacement which is given by equation 15 earlier should satisfy the following 6 equations therefore, right. That means u1 is equal to b1 plus b2 x1 plus b3 y1, u2 is equal to b1 plus b2 x2 plus b2 y2, and likewise that, and like the v3 is equal to b4 plus b5 x3 plus b6 y3, right. So, solving these equations, one can find the coefficient like b1, b2, b3 and all that, and b4 in terms of the nodal displacement and coordinates. Substituting these coefficients into the equation 14 earlier, and if you arrange all these things, one can get this equation number 16. So, this equation number 16, again same thing as I mentioned, that is the displacement vector have the shape factor multiplied by your when there is a u1 v1, u2 v2 and u3, because it is a CST element. So, the shape function, that is the linear function in x and y. Therefore, these shape functions, that is n1, n2 and n3 is given here, that like for an example, these all the shape function n1, n2 and 3 is given in equation number 17, like n1 is 1 by 2a, and then x1 y1 x2 y3 minus x3 y2 plus y2 y3 x plus x3 minus x2 y. Likewise, all n1, n2, n3 is shown here in 17, and A, which is the cross sectional area, is can be given as 1 by 2 determinant of this 1 x1 y1, 1 x2 y2, 1 x3 y3. This is shown here in 18. The A is in fact the area of the triangle. One you can prove it also, the area of the triangle, and this is written here in equation 18. Using the strain displacement relation, if you recall in number 8 equation, and that results into equation number 16 and 17, then one can write down here, that is the strain sigma x, sigma y and shear strain xy is nothing but capital B D vectors. So, capital V vector is this, and the displacement vector which was, and this is what is shown in equation number 19. In fact, x I j is can be written as x1 minus xi minus xj, and similarly yij, if it is written as yi minus yj for I and j to be 1, 2, 3. So, one can see that the constant strain within the elements. So, from stress strain relationship, that is equation number 5. For example, one can see that the stresses obtained using the CST element are also constant. So, you can verify it. Okay. So, applying the formula which was given in equation number 13, one obtain the element stiffness matrix for this particular CST element, and that is what it becomes, K is equal to over the integral on the domain, that is capital BT E B dV, and that is nothing but T A B T E B, that is shown here in 20, and in which your T is the thickness of the element. Note that the K, that is the stiffness for CST element, is a 6 by 6 symmetric matrix, okay, because the U1 V1 U2 V3 and U3 V3 6, so 6 by 6 matrix, symmetric matrix. The matrix multiplication of as of corresponding to equation 20 can be carried out by computer program, any program, simple program can be written. Both the expressions of the shape function which is shown in equation 17 and their derivatives are lengthy, and other little insight into the behavior of the elements are required. So, if you look at this figure, the normal coordinates, how it is shown. So, that is the natural coordinate. If we say as the zeta eta as the natural coordinate for this particular triangle, right, on the triangle, then the shape function can be expressed in terms of these natural coordinates, right. That means, and that is a very simple form. If you remember n1, n2 and n3 in x, y, z coordinate is a long equation, but if you introduce this natural coordinate system, it becomes very simple. Like here, the n1 is equal to zeta, n2 is equal to eta, and n3 is equal to 1 minus zeta minus eta. That is what is shown here in 21, subjected to the condition that your zeta is 1 at node 1 and zeta is 0 at node 3, right, and if any node is taken in between center, that is the AB, that is equal also to be 0, right. And similarly for the eta, on the node 3 it is 0, on the node A it is B, right, and on the node 2 it is 1. That is the by definition, and one can then note that n1, n2 and n3, sum of these must be equal to 1, which ensures that the rigid body translation is represented by the chosen shape function also in 1D case, because ni is equal to 1 or 0 at node I is 1 and everywhere it is 0 at other nodes. So, and varies it, that this ni varies linearly, as I told you earlier. So, one can see the plot also for the shape function ni, and this is quite simple, and this what has been shown here in figure. So if you look at the shape function Ni for the CST, the two coordinate system for the element, the global coordinate system xy and the natural coordinate system, that is zeta eta, the relationship can be established like here, that is in equation 24 and 25. So that's the x becomes your x 1 3 zeta plus x 2 3 eta plus x 3, y is y 1 3 zeta plus y 2 3 zeta plus y 3 for the third node, right, where your xij is the same definition as I told you, x4 minus xi minus xj, yij is yi minus yj, where for variation of I and j from 1 to 3. So the displacement u and v on the element can be reviewed as the function of xy or eta zeta using this particular chain rule for the derivatives, and this is what is has been shown in equation 26. Please note that the J is the Jacobian matrix of the transformation which is shown here. So if you use this equation 25, that is the relationship between the xy coordinate and the natural coordinate system, so J becomes this one, that is the x1 2 y1 and x2 3 and y2 3, and J inverse can also be obtained accordingly, that is in 27, where determinant J is nothing but x11 y21 minus x23 minus y12, and that is equal to 2a, and as I told, tell A is the area of the CST triangle, right. So from equation number 26, 27, 16 and 21, one can write down this value, that is the dy u by dy x, dy u by dy y, and that is what has been shown here in equation 28. Okay, that is 1 by 2a, and y23 minus y13 divided by minus x23 x13, and u1 minus u3 u2 minus u3, and similarly you can also find out dy v by dy x, dy v by dy y, and this is what is shown here in equation 29. Okay, so using the result in equation 28 and 29 and the relations, that is the strain relation, that is capital Du R, which was equal to capital D capital N D, and that is also capital B D, one can obtain the value of matrix B, right, that is what the strain displacement matrix capital B, that is what has been shown here as 1 by 2a, and this matrix, that is y230 y310 y120 0 x320 x 230 and x21, and x32 y23 x13 y31 x31 and y12. This is what is given the strain displacement matrix capital B in equation 30, and this is same as we derived in equation 19, please remember. So one can use this CST element for different applications, right. You can use it in area where the strain gradient is small. You can use in the mesh transition area, like fine mesh to coarse mesh, and avoid using CST in stress concentration of other crucial area in the structure, such as like edge of the solid, edge of some hole and corners, etc. So it is recommended for quick and preliminary finite element analysis of 2D problems, right. So if you look at this figure shows the case where it's a ANSYS case where uh, the CST element has been used, right. You look at the situation. In fact, the linear strain triangle are also very popular. We call as the apart from the constant strain triangle CST, we can also use linear strain triangle LST, or this is also technically called as T6 element. The element then we can take as a quadratic triangular element. There it was linear, the constant value, but here we take a quadratic triangle element. So if you look at this, so this is what's the basic quadratic triangular element, all right. So if you look at here, this is now total 3 6 element, total 6 element now, because it is now quadratic. So there are 6 nodes on this element. These corner nodes and 3 middle nodes, each node has 2 degree of freedom, okay. As explained before, the displacement u and v are assumed to be quadratic function of xy. Therefore, that means u is equal to b1 plus b2 x plus b3 y plus b4 x square plus b5 xy plus b6 y square, and similarly v is b7 plus b8 x plus b9 y plus b10 x square plus b11 xy plus b12 y square. This is what's the shown in equation 31, where as I told you, bi's, where the I is equal to 1 to 12 are the constants, and from these the strain can be obtained as, that is, the epsilon x is equal to b2 plus twice b4 x plus b5 y, and similarly strain y, and the shear strain is also, and these are shown in 32, and these strains are linear functions. Thus one has the linear strain triangle, we call it as LST, which is which provides the better result than the CST element. So in natural coordinate system, again you can convert this LST, and as the 6 shape function would appear, so like n1 n2 n3 n4 n4 n6, and these natural coordinate has been shown as in 33 question, where the say the zeta is 1 minus another term like what we call it, kappa is 1 minus zeta minus eta. So each of these six shape functions represent a quadratic form of on the element as shown here. So this is what the variation is, quadratic in nature. There it was linear, it is now quadratic. So shape function. So and then again the displacement is defined as shown in 34. So summation of all the shape function and multiplication with the corresponding values. So the the element stiffness matrix is still the same, K integral over the element BT E B dV, but here BT E B is quadratic in x and y. In general, the integral has to be computed numerically, right. So, the linear uh, uh, that we have seen, the triangular elements corresponding, there is in fact a linear quadrilateral element, we call it as the Q4 quadrilateral element. So, quadrilateral element linear if it has 4 nodes, right. So, this is what is have been shown, a linear quadrilateral element. Okay. So, there are 4 nodes at the corner of the quadrilateral shape. In the natural coordinate system, that is zeta eta, the 4 shape function is shown here in 35, equation number 35. So, that is n1, n2, n3 and n4 for this linear quadrilateral element. Please note that sigma I is equal to 1 to 4, n i's must be equal to 1 at any point inside the element, as which is expressed as the u and v, which is shown here in 36. So, which is in fact a bilinear function over the element in this direction as well as this direction. So, it is bilinear. The quadratic quadrilateral triangle also exists, just like we have seen the quadratic triangular element. Similarly, the quadratic quadrilateral elements, which we call it a Q8, is also there. So, we have then there are 8 nodes for each element. So, 4 corner nodes and 4 the inside nodes. In the natural coordinate system, that is zeta eta, then one can have the 8 shape functions, that is n1 to n8, and this is what has been shown here in equation 37, all right. So, again please note that the summation of all these shape function, if I say that is I is equal to 1 to 8, that is ni must be equal to 1 at any point inside the element, and the displacement field is given as equation number 38, alright. So, this quadratic function over the element, so the strain and stresses over a quadrilateral element are linear functions which are better representation. So, one has to remember that Q4 and T3 are usually used together in a mesh with linear elements. Q8 and T6 are usually applied in a mesh composed of quadratic elements. Quadratic elements are preferred for stress analysis because of their high accuracy and the flexibility in modeling complex geometry, such as curved boundaries if it is there in any case. So, this point are to be noted. Let's take one more example here. So, this is an example where a square plate with a hole at the center and which is subjected to pressure in one direction only, like here the pressure is in this direction. So, the dimension of the plate, let us take it as 10 inch by 10 inch, the thickness is 0.1 inch and the radius of the hole is 1 inch. If we assume E, the material value as 10 multiplied by 10 to the power 6 psi, and the Poisson's ratio to be 0.3 and the pressure to be 100 psi, the maximum stress in the plate, let us find it out, right. So, let us use finite element analysis as we have discussed so far, utilization of CST, utilization of triangular element, utilization of quadrilateral element, of linear as well as quadratic nature. So from this knowledge of stress concentration for this example, we should expect the maximum stress that occur at points A and B on the edge of the hole. This point A and B has been shown. Values of this stress should be around 3p, that is around 300 psi, which is the exact solution for an infinity for any very large plate with a hole inside. So we have one can try with say the FEA analysis using ANSYS for modeling this case, that is the meshing and analyzing. So using, if suppose one uses the quadratic triangular element T6 or LST, the linear quadratic element, that is Q4, and quadratic quadrilateral triangle Q8 elements, and let us use ANSYS to analyze this one, right. So the linear CST or T3 is not available in fact in ANSYS, so let us forget about. So what we would do, the stress calculation are done using ANSYS, using the different elements like T6, Q4, Q8, etc., and all these, and discretization and all that was there, and these all has been put together in this table, right. So the number of elements and degree of freedom used are shown here. So for an example, if you take the T6, the number of elements are 966, degree of freedom is 4056, and the maximum stress is found to be 3101. And if you look at this here, for the Q8 it is 322.3, right. Here T6 it gives 310.1, this gives Q8 gives 322.3, Q8 further at the earlier it was 320. So that's the one can check the deformed shape of the plate as well as in the even the simulation one can check in ANSYS. So check the convergence of using a finer mesh if possible. You can use lesser element as well, 100, say the 100 elements should be enough to achieve the same accuracy with the better or the smarter meshes are also used. So one can do the same exercise also later for the symmetric condition if it is there. So this is what's the result of the ANSYS, right. This result shows for Q8 element where the 493 elements are used. So that's the mesh. Upper one shows the mesh of the quadrilateral using the Q8 quadrilateral element, and this is what the stress distribution, the plot for the stress is shown here. So you can see the result. Okay, so this is what the basic we started with the basic element, 2D element, and took the example. We then the formulation part, and then to show you result by ANSYS, this shows the accuracy. Likewise, you can also try with similar kind of problem and practice on your own using ANSYS, which is popularly available in all the labs today. So you can try with, and hopefully we would continue the same lecture in lecture number 38 also with more examples, with more types of elements and other situations. But please remember that the finite element method using a software is not an excuse. If you work out the problems on these formulation basis, you first choose calculator and do it and find it out all again and again. You may take more and more time, but you will go inside the problem, you will go inside the steps that you do. You make a small programs yourself in C language or Fortran language and run it, because their problem comes, then you will appreciate the use of finite element method. Using a package is a quick solution, as I told you. These packages correct, but unless as a student, if you take this formulation, do it yourself, go inside what is happening inside by doing it by calculator and yourself, don't worry for the time. Practice more and more. If you practice one, then only you will come to know and you will appreciate the role of finite element method. All right, so hopefully you will be careful about all these things, and thank you once again. Thank you very much.